For the next hour or so, I want to be talking about discovering mathematics, and there will be quite a few. Interactive elements. I will send you a link in the chat when we get to it, and feel free to post any questions or comments or any other suggestions you have during the presentation. Okay, so let's get started. In the last few weeks, I've seen lots of images, kind of like this on Twitter, that map out a student's journey through mathematics. You start with simple things like place value, and then continuously add more and more complex topics along a simple and very linear path like this. And that's not just the case for school mathematics. In almost all university courses, you also start with the most basic axioms, and then build up more and more lemmas and theorems to arrive at more complex results. Of course, this is nothing how mathematics was developed throughout history, which probably looks a lot more like this. Many discoveries were random, accidental, and nonlinear. Most of the work done by mathematicians and scientists throughout history was actually incorrect and led to dead ends and was soon forgotten. Only the few correct results or interesting theorems were written down and then remembered in later generations. The same is still true today, not just in mathematics, but in all sciences. Only 14% of all published scientific papers are about negative, unsuccessful results, even though the majority of all experiments and studies fail, at least initially. And this led to a big push recently in the research community to change how we share these negative results. And a linear, sanitized version of the curriculum might be the most efficient way to prepare students for exams if you don't really care about anything else. But I think there are two important reasons why we shouldn't do just that. The first one is that we want to give students confidence. We want to show them that it's okay to make mistakes and that it takes time to understand new ideas. And the other one is that we want students to be able to solve realistic, real-life problems, and we want to inspire them to explore, discover, be creative, question their assumptions, and become critical thinkers. So in this presentation, I'll go through lots of examples from history, interesting puzzles, which you can solve as well, and hopefully you enjoy that. And a great point to start are number systems. Numbers date back thousands of years, of course. The first known number system was in Mesopotamia, the base 60 system from around 3400 BCE. In ancient Babylon and Egypt, mathematicians also developed some basic types of fractions and rational numbers. In ancient Greece, numbers were mostly things that could be constructed geometrically. For example, you've got a line of length 1, you can find the midpoint, and then you've got lines of length 1/2. This is sort of how you could construct the fraction in 1/2. Could also have a square of side length 1, and when you draw the diagonal, it has length square root of 2. So Greek mathematicians had discovered irrational numbers. But rather than being excited by this new discovery, they were actually terrified. Pythagoras allegedly called irrational numbers unspeakable, and his followers, the Pythagoreans, tried to cover up their existence and possibly even murdered members who shared this dangerous secret. Some of the later Greek mathematicians were pretty okay with irrational numbers, but there were still no negative numbers. Diophantus in the 3rd century referred to equations with negative solutions as absurd. Instead, negative numbers were started to be used in China and India. Around 630, the Indian mathematician Brahmagupta used negative numbers to come up with the quadratic formula. And a few centuries later, Arabic mathematicians were also starting to become familiar with negative numbers. And this time here in Europe, we were still using Roman numerals and no fractions, no negative numbers. And this is when Leonardo Fibonacci, who you might know from Fibonacci numbers, traveled with his dad, who was a merchant around the Mediterranean. He He went to the Middle East, he heard about the decimal number system and negative numbers. And when he returned to Italy, he published a book about them. It's called the Liber Abaci, and it's probably one of the most significant publications in history introducing decimal numbers to Europe. But still, even in the 17th century, long after Fibonacci, people didn't really believe that negative numbers existed or even made sense. Okay, but even with rational, irrational, negative numbers, our troubles aren't quite over. Around 1545, the Italian mathematician Girolamo Cardano invented a new kind of number to solve certain polynomial equations that weren't possible to solve before. And a century later, in 1637, René Descartes gave these numbers a name, imaginary numbers. And he picked this name, obviously, because he didn't believe that these numbers really existed. He thought they were just made up. And again, it took centuries for mathematicians to discover the importance of these imaginary numbers and how real they actually were. And even in around 1880, Georg Cantor was thinking about different kinds of infinite numbers. He was called a scientific charlatan, a corrupter of youth, by prominent mathematicians at the time. And today his results are taught in every undergraduate mathematics course. This all goes to show that even in a precise, logical subject like mathematics, there was a huge amount of debate and controversy throughout history. And also, it might be unfair to expect students to understand crucial topics like negative numbers when it took humanities many centuries. Okay, let's think about geometry. We all learn about Euclid's 5 axioms in school, and usually it's one of the very first lessons in any geometry textbook. You memorize them, and then you can use them to prove more complex results and theorems later. Of course, that's exactly the opposite of how Euclid worked. He and other mathematicians at the time started with the more complex results, played around with geometry, made certain observations, and then worked backwards to find out which axioms were needed to prove all of these results. And again, there was a significant amount of debate around some of these, especially the last one, the parallel postulate. Euclid's book, The Elements, became the standard textbook in mathematics for almost 2000 years, and his axioms were incredibly powerful. But it turned out that there were certain problems that were impossible to solve just using Euclidean geometry. Trisecting angles, for example, doubling the cube, or squaring a circle. And for example, doubling a cube essentially corresponds to constructing 2 lines with the ratio, where the ratio is the third root of 2. Countless mathematicians tried solving these problems, but were unsuccessful. And of course, every angle must have a third. So we kind of have to question whether we just haven't tried hard enough to find a solution, or whether there's something wrong with Euclid's axioms that prevents this from being possible. And one thing you might have noticed about Euclid's axioms is that there's one important concept missing: units. There are no distances, areas, or even angle sizes other than right angles. You can determine whether 2 lines have the same length, but not what this length actually is. And there's a simple reason for that. In ancient Greece, there weren't any accurate measuring units. People were using the length of the hand or their arms to sort of roughly measure distances, but nothing accurate enough to fit into Euclid's idealized world of mathematics. Of course, thousands of years later, that has changed. And René Descartes didn't just name imaginary numbers, he also developed Cartesian geometry, the first sort of big step since Euclid. And for the first time, this allowed us to use algebra to solve geometric problems rather than just straight edge and compass, and made it possible to trisect angles or even square the circle. And remember Euclid's 5th axiom. About 200 years after Descartes, 3 mathematicians, Gauss, Bolyai, and Lobachevsky, were thinking about what happens if the 5th axiom did not apply. And almost simultaneously, they all discovered spherical and hyperbolic geometry, what we now call non-Euclidean geometry. And this shows us how important it is to question assumptions, even if they've been around for many, many centuries. And today, spherical geometry is used everywhere, from satellite orbits to map projections. Talking about maps, How many colors do you need to color a map like this if adjacent states or countries are not allowed to share the same color? You might know the answer, you might have seen this problem, but we've actually made an interactive version of this for you to play around now. So if you go to this URL, I'll also put that in the chat, math.fit/conf, you get to a website where you can play around with this and try it out yourself. And I see Rob just brought up the first poll of the session where you can answer the question. So I'm also going to share a different window if this is working. So if you go to math.fit/conf, you should get to this website. We've got an interactive version of these maps. You can pick different colors. You can start coloring in states or counties of England. You're not allowed to color adjacent counties like these two in the same color, for example. That's not possible. And it tells you at the top how many colors you've used. So we'll just wait for a couple of minutes for you to play around with this. And yeah, please do answer the poll to say how many colors you think are necessary for all of these different maps. So we're only looking at the first question in the poll right now. And question 2 and 3 are later in the presentation. I hope you can submit the poll with just the first question, not all of them. If not, just put your answers or thoughts in the chat panel and we'll see those. So we're seeing lots of fours in the chat. Let's see, I'll try South America myself. 2 colors so far. We need a third one, and we might even need a 4th color here for Peru, but hopefully we're okay now. Like this. So 4 colors seem to work for South America. Okay, I'll switch back to my slides. Don't close the browser window just yet. We'll need this again later in the presentation. And also don't click the next step button at the bottom unless you want to peek ahead and at what's coming next. I'll switch back to the slides. So many of you probably know the answer. It is indeed 4. It's called the 4-color theorem. And it actually dates back to 1852 when the South African botany student Francis Guthrie was trying to color in a map of counties of England. And he noticed that 4 colors were enough, and they were enough for any map he tried. But he couldn't find a proof that this always worked. But a few years later, Alfred Kempe found a proof that 4 colors are always enough for any map you try. And a year later, a second proof was found by Peter Guthrie Tate. Even better, we've got 2 different proofs for the theorem. It clearly must be true. Unfortunately, that's not the end of the story. About a decade later, people found a mistake in Kempe's proof, and it couldn't easily be fixed. Kempe's proof did not work for the 4-color theorem. And the next year, another mistake was found in Tate's proof. It was also wrong. Oh no, people thought for a decade that this problem in mathematics had been solved forever. But this is clearly not the end of the story. In fact, it took almost a century and the invention of computers until 1976 to finally prove the 4-color theorem and show that 4 colors are always enough for any map. And this was done by Kenneth Apple and Wolfgang Haken using this IBM supercomputer to try lots of different special cases. And they actually used 1,200 hours of compute time to find the result. And this was the first major theorem in mathematics ever to be proved using computers. There are other examples in the history of mathematics where important mistakes went unnoticed. In the 19th century, one of the most important problems that mathematicians were thinking about was the three-body problem. Calculus had been around for some time, and it's relatively easy to determine what happens when two bodies, like the sun and a planet, orbit around each other in space. But as soon as you add a third planet or moon or something else, things get a lot more difficult, if not impossible. And we've got, if you now click next step on the website, we've got an interactive version of this. I'll show you 1 second. So we've got 3 different planets. They all have some initial speed, and we can click play and see how the motion of these planets works initially. And you can also move the initial position of the planets if you want to. But just wait for a second at what happens. So it starts out really nice in a stable equilibrium, but after some time, the motion just becomes incredibly complicated and almost chaotic. So yeah, you can reset the position, you can move them around a little bit and see what else you can find. Meanwhile, I'll switch back to my slides. So like I said, this was one of the most important problems that mathematicians were thinking about in the 19th century. And around this time, King Oscar II of Sweden established an international mathematics competition to honor his 60th birthday. And one of the 4 problems in the competition was the n-body problem. So not just 3 n-bodies. And one of the leading mathematicians at the time was Henri Poincaré from France. He tried to solve this question, and although he didn't strictly solve all of it, the judges were blown away by his work. He made some really big progress. So Poincaré received 2,500 kronen and a gold medal as the award. And his submission was due to be published in a mathematical journal. The printing was already in progress. The printing presses were running when Poincaré sent an urgent telegram to the editor. He had found a mistake in his proof. And soon it became clear that there wasn't an easy way to fix his mistake. Poincaré was very distressed at the time. He asked whether he should return the prize, but the judges thought that this wouldn't only harm Poincaré's reputation, it would also harm their own because they didn't spot the mistake. So it would also humiliate King Oscar and this prestigious competition. So instead, what they did was they tracked down all of the copies of the magazine that had already been sent out, and they destroyed them. In fact, even today, only 2 copies of the magazine have survived. Poincaré wrote a significantly revised version of his submission that makes some big assumption and much less important results at the end. And he secretly had to pay for the printing of the first magazine that had to be destroyed. And that was even more expensive than the prize money he received in the first place. Today, we know that there isn't a simple solution for the 3-body problem. It's completely unpredictable, and Poincaré had actually laid the foundation for chaos theory that should come about a century later. And something very similar happened to Andrew Wiles just recently. He had just revealed his proof of Fermat's last theorem, one of the most famous unsolved problems in mathematics at the time. The proof was incredibly complex, and only a few mathematicians were actually able to understand and verify it. And one of these people hired to check the proof found an error. And again, initially it seemed just like a rare edge case, but it turned out to be a very serious flaw. Even worse, now if someone else could find a fix for just this small error, they would get all the credit for solving Fermat's last theorem, despite of Andrew Wiles's previous work. So secrecy, once again, was important. It took 1 year, but unlike Poincaré, Andrew Wiles was indeed able to fix the flaw in his proof and to go down in history. Now, all this goes to show that even the greatest mathematicians in history make mistakes, have misconceptions, and take a long time to accept new ideas. This can be a great way to tell students about history, give them and to give them confidence. But so far, it doesn't really allow students to make their own discoveries. So in the next half of the presentation, I'll talk about a few more examples that should be really accessible for students. And the first one, again, it's a problem you might know, dates back to 1736. At this time, the famous mathematician Leonhard Euler moved to Königsberg, a city in Eastern Europe, and he learned about a puzzle that had been bothering the people of Königsberg for a long time. Is it possible to walk around the city in sort of a continuous route, cross every one of these 7 bridges you can see here, but not cross any bridge more than once? And again, click next at the bottom of the website. We've got an interactive version of this to try out yourself. And is this working? Nope. Try again. I hope you can see a different screen now. So click next step and we get to the bridges of Königsberg. This is a map of Königsberg at the time with the 7 bridges, and you can actually try to draw a path. The bridges turn green once you've crossed them so that you don't cross them again. And you can see now I'm sort of stuck. I can't get to the last bridge without crossing one of the other ones a second time. But so see if you can find a solution for this map. But if you can't, we also have a few others for you to try out. And yeah, it doesn't matter where you start. You can start on any of the different islands. You just can't cross a bridge a second time. So there's the second poll question should be about this. You can check which of these 4 maps you think are possible, which ones you can't find a solution for. And again, I'll give you a couple of minutes to play around with this. It's the same link like at the very beginning. You always just have to click next step at the bottom of the page, but I'll also paste the direct link in the chat panel in case you accidentally close the window. Remember to try different starting positions if you can't find a solution from your initial island or bank of the river. That might make a difference. And yeah, I'm just reading the chat. Simon Singh's book about Fermat's last theorem is really amazing. And it's actually, fun trivia, what inspired me to study mathematics at university. If you have a touch screen like an iPad or even phone, you should be able to use this on a touch screen, which might be easier than a trackpad. So obviously, keep trying, keep playing around with this. I think I can't see the results of the poll, which is a bit unfortunate. But I think there should be solutions for the 2nd and 3rd map, which you can find relatively easy. But you might struggle with the 1st and the 4th map. And the first one, obviously, is Königsberg. Euler wasn't able to find a solution, a path that crosses every bridge once and not more than once. But what he did manage to do is find a proof that it is indeed impossible. So if you don't have a proof, people might obviously say, oh, you just haven't tried hard enough, you haven't found the solution. But this proof is actually pretty accessible even to GCSE students. And with a little bit of guidance, they can come up with the proof themselves. And this puzzle shows us some really important strategies when trying to solve new problems like this, which aren't really related to anything else you've done in mathematics so far. One important point is you have to try many examples. You've got to try simpler versions or specific edge cases. So maybe just a map with 2 islands and some bridges between them, or just 3 islands and bridges between them. Try to simplify it as much as possible to really find the underlying patterns. You also can try to abstract the problem and remove any unnecessary detail. For example, rather than thinking about islands and bridges, you could think about points and lines, and you just have to connect different points with lines, and that might make the problem a lot simpler to think about. You have to represent objects in different ways, make abstractions, and of course it helps to think which other areas of mathematics might be helpful, even if initially they seem completely unrelated. So we've got a second problem of this. Again, click next step at the bottom of the web page to get to this, and this is called the 3 utilities problem. It's a similar idea. In this case, we've got 3 factories, water, gas, and electricity, and we've got 3 houses. And we have to connect each of the houses to each of the utility companies. But, and this is important, the lines are not allowed to overlap. So we could connect water here, I could connect electricity here. I can't connect this house like this now, because then the 2 lines would overlap. So let me start again. I could maybe connect it like this and then go around. So I've got to connect each of the 3 houses to each of the 3 factories. And again, I'll give you a little bit of time to play around with this and see if you can find a solution. And I don't think we have a poll question for this, so just post in the chat if you manage to find a solution. Maybe you can even share a screenshot if so, or if you can't find a solution. Okay, some really interesting comments in the chat. If I printed it on a mug, I could give you a solution from Carrie Martin. Patricia also thinks it could be done if it's put on a torus. Anita thinks it's really hard, but she doesn't have a mug, I assume. It's just a sort of 2-dimensional version here. We can go 0 carbon if it works from Carl. So close, yeah. It is not easy, definitely. So we still need this connected to water like this, and now we have to connect this last house to gas, and doesn't seem like there's a way to get to the gas company. All of the ways seem to be blocked. Miranda also thinks it can't be done on a plane. And Carrie, Patricia, Miranda, you are all right, obviously. This problem, just like the Königsberg Bridges problem, is indeed impossible. It's not possible to connect these 3 factories to these 3 houses without having any lines that overlap. And if we sort of go into more advanced mathematics, this is called a bipartite graph, and it's not planar, so it can't be drawn on a plane without any of the lines overlapping. Remind people to change the drop down to all panelists. Oh yeah, if you post in the chat, change the blue drop down to all panelists and attendees, so that everyone can see your answers. If you just have just panelists, I'm the only one who can see the answers. So yeah, like Königsberg Bridges, the three utilities problem is not impossible. And this is also an important lesson for students to understand. If all you ever do in school is solve diagnostic questions or past exam problems, it's very easy to get the impression that every problem in real life has a solution, and you just happen to know everything you need to find that solution. But as we know, nothing could be further from the truth. First of all, you often don't get a precisely defined problem in real life. You first have to ask the right questions and write your own problem, maybe. Then you have no idea whether a solution even exists and how hard it is to find them. As we saw before, it sometimes took centuries of further research in mathematics before it was possible to solve a relatively simple problem. You have to examine any assumptions you've made, like Euclid's fifth axiom, and maybe removing a certain condition or assumption breaks the problem or suddenly makes it possible. And then you know that this assumption must have a key impact on what's going on. For example, as people mentioned in the chat, if the three utilities problem is actually possible if you do it on the surface of a coffee mug. And in that case, you can use the handle of the coffee mug kind of as a bridge to allow two different connections to cross. If you still can't find a solution, you might have to make certain approximations and simplifications to the problem. That doesn't apply just in mathematics, but also in science, technology, economics, and many other cases. And critiquing and justifying these assumptions requires a very different set of skills, but one that is just as important as just sort of basic algebra and geometry. Discovering mathematics might almost feel like exploring a dark room. You have no idea what to expect, but you can slowly feel out different shapes and objects. And there might be some frustration initially, but also great surprise and wow moments when you stumble upon something completely unexpected. And hopefully we'll have some of these wow moments later in this workshop as well. Here's another great example that's accessible to even primary students. Perfect numbers are numbers like 6, which are equal to the sum of all of their factors other than itself. So the factors of 6 are 1, 2, and 3, and 1 plus 2 plus 3 just happens to be 6. Does anyone know what the next perfect number is? Feel free to post that in chat. Maria, Patricia, Katie, Nikki, lots of people say 28, and that is indeed correct. So the factors of 28 are 1, 2, 4, 7, and 14. And if you add them up, you do get 28. After that, things get a little bit more difficult. The next one is 496, then 8,128. And these numbers grow rapidly, as you can see. But we don't have to calculate them ourselves. We can use computers to do stuff like that. But just by looking at these first couple of perfect numbers, what do you notice when looking at them? 6, 28, 496. What do they have in common? Do you see any patterns like this? And again, just post your answers in chat. They are all even. Last digit, says Gian. Indeed, so the last digit always seems to be a 6 or an 8 in this case. Keith has found, remembers the, I don't know how many trillion or quadrillion it even is. The last couple of digits, so lots of people are saying all of these perfect numbers are even. The last digit is always a 6 and an 8. One thing that's a little bit harder to spot, but it's also true, is that all of these are triangle numbers. So you can sort of arrange them in dots in a triangular shape. And mathematicians have found a proof that every even perfect number must indeed end in a 6 or an 8. But they've not been able to find a proof that every perfect number is even. And using computers, we've checked, I think, numbers up to 10 to the power of 1,500. So that's the one with 1,500 zeros. It wouldn't even fit on this slide. But and all of trying all of these numbers, we found that all of the perfect numbers are indeed even. But of course, that's not equal to proof. There might be a perfect number just after 10 to the power of 1,500. That's odd. And people have been thinking about this for a very long time. This problem dates back to some mathematicians in ancient Greek. I think Diophantus, which we also saw earlier, he was the one who didn't believe that negative numbers exist. But he was thinking about perfect numbers. I think he knew the first 3 or 4 of them. he was trying to find a reason why they all have to be even, and he couldn't. And since then, all of the smartest mathematicians throughout history have tried this problem and failed. We still don't have a proof. We still don't know whether there are any odd perfect numbers. And this actually makes it the oldest, still unsolved problem in mathematics. And even primary students can understand it, but the smartest thinkers throughout history have not been able to find a proof. And Wikipedia has an entire page with hundreds of unsolved problems in mathematics, and quite a few of them are accessible to primary or GCSE students, like the perfect number problem. And this is a great way to show students that mathematics isn't finished, with important research and new discoveries happening all the time, still now. And particularly in mathematics, this can actually be quite scary, because in 1931, Kurt Gödel proved that some problems in mathematics are impossible to prove. It's called the incompleteness theorem. And this doesn't mean that they are really hard or that they require some new tools and discoveries that haven't happened yet. It means that they are actually logically impossible to prove given a specific set of definitions or axioms. And when you start a new unsolved problem in mathematics, you have no idea whether it might be one of these impossible problems that you can never find a solution to. So this can be quite scary. But as sort of the last section in this workshop, I wanted to give you the chance to discover some mathematics. And I hope that some of you won't have seen this before and will be amazed. And again, you can participate, of course. So this example is about sequences and convergence. We all know what a recursive sequence is. We sort of define the next term as a function of previous terms. And in this sequence, we just square the previous number every time to find the next term. And for recursive sequences, I, of course, always have to tell you the starting point, x0 in this case. And once you know the starting point and the recursive equation, you can just calculate all following points in that sequence. And we can think about what happens to the sequence for different starting points. So like, as you can see in this example, if the starting point is between -1 and 1, the numbers will get smaller and smaller and converge to 0 eventually. If the starting point is less than -1 or bigger than 1, the numbers will keep growing and growing and growing forever. And we say that the sequence diverges. If it happens to be exactly -1 and 1, it would also converge and just sort of be the same number all over again. So I've highlighted along this number line the region where the sequence converges, or at least where it doesn't diverge, in blue. And earlier in this workshop, we also talked briefly about complex numbers and imaginary numbers. And many of you might know that we can represent imaginary numbers in a coordinate system. So we've got the real numbers along the x-axis, we've got imaginary numbers along the y-axis, and any other point in the coordinate system represents two complex numbers. So this intersection here, I hope that you can see my cursor, for example, would represent, correspond to 1 plus I. And again, you can try this yourself, but it should be relatively obvious. I've colored all of the points in the complex plane where the sequence converges. So as long as the complex number is within this unit circle of radius 1 at the origin, the sequence will converge and get smaller and smaller and converge to 0. If you start somewhere outside the circle, the sequence will get bigger and bigger and diverge. So far, we've not really seen anything particularly exciting or new. So let's make this sequence a little bit more interesting. Rather than just squaring the previous number, let's add a new complex number c at every step. So we start with a number, we square it, we add c to get the next one, then we square it again and add c, we square it again and add c, and so on. So in this example, c is just 0, we don't add anything. But what happens if I add a different number at every step of the sequence? How do you think the shape of this blue area would change? And we should have the last poll question about this, but you can also just put some ideas or suggestions in the chat. So maybe we would see an ellipse rather than a circle that's sort of stretched in the direction of C. Or maybe we would see 2 or 3 circles. Maybe we don't see any circles at all. Maybe it's a polygon or sort of rounded square, or maybe something completely different. Yeah, answer the poll or just put your suggestions in the chat and we can talk about it. Rob, is there, I can't actually see the results of the poll. Is there anything I have to do to see that? We are still thinking. Yeah, so if your answer would be something else, sort of the last question, just post it in the chat. And you definitely don't have to be scared of making wrong suggestions. That is absolutely the point here. And as we've seen, mathematicians have made so many mistakes throughout history. It's in fact actively encouraged to make mistakes and try things out. So Hannah thinks it might be polygon with sort of rounded edges, I guess, or circular edges. Oh, I could just about see the poll for a second and then it disappeared. Let's see if I can bring that up again. There we go. So some people think it's a circle with a shifted center. Lots of people think it's something else. So what is something else? Post that in the chat. So maybe it stays the same size, but is translated. Mr. Al-Hassan thinks that. Catherine thinks the circle moves, but doesn't know which way it might go. Okay, looks like Chris has peeked ahead on the website and noticed that this pink circle here is actually interactive, and this is the position of C. So right now it's at 0. And again, click next step on the website and we can actually see ourselves what happens. So we've got the circle here. This yellow point is the starting point, and you can sort of see if we start somewhere inside the circle, the sequence converges to 0. If we start outside the circle, the sequence diverges, and sort of that's the difference. But let's ignore the yellow point for now and move this pink point in the middle. This is the point C that is added every time after we square the previous number. And I want all of you, I wish you could all turn on your audio. I want to hear what you think. If I just, what your first reaction is. If I move this circle a little bit, it kind of is an ellipse, but not quite. And if I move it a little bit further, we get these really beautiful spirals happening. Something completely unexpected, sort of these little circles nested. And obviously, this is a pretty rough sketch so that it can run on phones and so on. But yeah, just spend a couple of minutes playing around with this and see what. So sometimes it always converges and the entire plane is white, like here, for example. Let's try what else we can find just by moving this pink point. And remember that all of these incredibly complex, infinitely complex, in fact, shapes are created using a single simple equation and complex numbers. So this is a pretty powerful result. And all of these pictures on your screen right now are dynamically generated using a relatively simple computer or even tablet device. But I can show you in my slides what these images look like if we can actually run these computations for a longer amount of time. They are called Julia sets, named after a French mathematician, Gaston Julia, who first explored them in the early 20th century. So this is a really beautiful example of what they look like. And in this case, the different color gradients represent how quickly the sequences diverge, not just the sort of binary yes-no state. Here's another really beautiful example of what these infinite Julia sets look like. And you can see they are fractals. We'll get to that in a second. But one thing you can see is that they are self-similar. So if you look at this entire bottom half of the Julia set, it's repeated over and over again at just smaller scales. So this smaller copy should be exactly the same. And Rebecca asks whether this is the Mandelbrot set. It's not the Mandelbrot set, but it's very closely related. So, and in fact, I'll switch my screen again. This is becoming a habit, but if you click next, you can try the same thing with the Mandelbrot set. So remember, in the last time we fixed the value of C and then colored the entire complex plane by moving the value of x0, the first position in the recursive sequence. Let's invert that. Let's fix the value of x0 at the origin at 0, and instead move the position of C and color the plane by if this value of C means the sequence diverges, we color it white, otherwise blue. And this you have to sort of do yourself. You can move the position of C and see what you can find as you move it around the plane. And in this case, you do get the Mandelbrot set, which again has a lot of similarities with the different Julia sets, but looks a bit different. But again, you see these nested circles, a big cardioid in the middle, and you can sort of discover on your own what this looks like. And one really interesting thing to think about when you do these interactive games is that at the time when mathematicians first started thinking about these fractals in the early 20th century, there were no computers to visualize them. They could predict some of the properties using mathematics, but they were never able to see exactly what these fractals actually looked like and how beautiful they are. This took about 50 years later until sort of Benoit Mandelbrot came along and used computers. And I can show you one of the first ever images of the Mandelbrot set like this, sort of just a collection of X's on a computer printout. And at the time, computers filled entire rooms, and the printers of computers were operated by special technicians. So this was, I think, around 1970. And when Mandelbrot first printed copies of the Mandelbrot set, the technicians thought that some of the roughness and irregularity around the edges was actually caused by printer errors, and they just cleaned it up and removed it. And it actually took Mandelbrot several attempts and several tries to figure out what was going on, because the printouts he received from the technicians were completely different from what he was expecting. And like all fractals, you can zoom into the Mandelbrot set forever and always discover new patterns. And again, this should be the next step on the website. Here you can move the slider at the bottom and zoom into the Mandelbrot set forever. Well, not forever in this case, but pretty far, I think, several trillion times of magnification, and yeah, discover all sorts of different patterns. So this is a little Julia set island hidden inside the Mandelbrot set. And you can just keep going. And rendering these images took I think about an hour on my laptop to generate them. So yeah, have a little play around with this. You can obviously, there's a lot of software around to generate your own fractals if you're interested. But I wanted to show you one final example called the chaos game. So again, click next at the bottom, you should get to this chaos game website. Again, it's a way to generate fractals. In this case, we start with a triangle. We pick one of the vertices at random, say the red one. Then we pick one of the other vertices at random, say the yellow one, and draw a dot halfway in between the 2 points. And then we repeat this step over and over again. We start with our new midpoint we've just drawn, pick one of the 3 vertices at random, like the green one, and draw the midpoint, which would be somewhere here, probably. And in this interactive, you can do this 5,000 times in one go. And you can see, again, using a really simple set of rules, just drawing midpoints all over again, you get this really beautiful fractal pattern. This is called the Sierpinski triangle. But of course, we don't have to sort of stop at that. We could try using a square, for example, rather than a triangle. And now if we do it, unfortunately, nothing interesting happens. So again, just because a specific rule works in one case, it doesn't always have to be the case. And many of the examples you will find don't look particularly interesting. But again, I'll just reset the screen. Let's try to maybe use a different ratio, maybe use 2/3 instead of 1/2. So in this case, we draw the points 2/3 along the line between the two previous points rather than halfway. And in this case, oh yeah, we get something slightly more interesting. So again, there's no exercise or poll or answer in this case. I just want you to spend a couple of minutes to play around with this. We've got a few different rules. So maybe you can also pick midpoint of the edges. Maybe you can also include the center of the polygon you have. You can actually move the position of the vertices of the polygon. So if you don't want a square, you want a different type of quadrilateral, you can do that. You can play around with pentagons. You can combine several of them on the same diagram. So we can have a small triangle like this, small Sierpinski triangle, and then draw a second one sort of along the side. Just play around with this and see if there are any other really beautiful or interesting patterns you can discover. Kim missed the beginning due to a technical issue. So we're looking at a fractal game called the chaos game, which is a way to generate fractals. So let's use the square as an example. We've got 4 vertices. We pick one of them at random, then we pick one of the other vertices, and we draw a dot at a certain distance along the line between the 2 points we have. And this could be halfway, it could be 2/3, it could be the golden ratio. So you can pick different ratios. And then we repeat that same step over and over again. So pick another vertex, draw the midpoint or point 2/3 along the way, and over again. And you can do that 5,000 times just by clicking this button and see what other patterns you discover. So how about we've got a square, we've got the ratio of 2/3, and we also include the midpoints of the edges of the polygon. In that case, we get a really nice fractal. This is called the Sierpinski carpet. It's sort of a square version of the triangle we saw before. Or we could look at the pentagon, could use the golden ratio and maybe include none again, simple version. And we get these nested pentagons, almost like a snowflake, maybe. So lots of really beautiful patterns you can find using, again, a really, really simple rule that should be accessible to primary students, GCSE students, and that allows them to make some discoveries themselves and discover their own personal fractals. You can make them by hand, obviously, but it takes a lot of time. So you need around 5,000 steps before you get the full picture. So that might be a little bit hard by hand. But you could use a programming language like Scratch, for example, and allow students to write a computer program that generates them these patterns itself, kind of like what I've done on this website. And that might also be an interesting way to bring a little bit of computer science in. Yes, so Anita said she did this manually using a dice to decide which of the 3, 4, 5 vertices to pick. And yeah, we always need to randomly pick one of the vertices. We can't always pick the same one, obviously. And dice are a great way to sort of randomize this. But again, like you mentioned, that does take a lot of time. So maybe you can do the first 50 steps by hand and then use a computer or programming language to generate all the remaining ones. Okay, so we are almost out of time. But before I end, I just wanted to show you a very short video. All of the interactive elements, Yvonne, I think you would be able to do this in GeoGebra, definitely. And in fact, if you Google GeoGebra Chaos Game, you'll probably find some worksheets or existing GeoGebra files that have this built in. But all of the interactive games and simulations you've played with in this workshop are from a website called Mathigon, which is what I've been working on for the last couple of years. It's an interactive online textbook for GCSE and A-level mathematics. And I'll just show you a very short video that shows some of the other exercises and examples and activities we have. So hopefully this is playing. If Zoom. So here's, and it's playing a short video that shows some of the activities, exercises we have on Mathigon. It's completely free to use. It works offline on mobile apps or just on the website. You don't even need an account to try it out. And our goal is to try to make learning as interactive and colorful as possible. So all of the diagrams are interactive. You can move the points. At every step, students have to participate, explore, play around with different activities. You can search the first million digits of pi to find your birthday. Lots of three-dimensional diagrams like this. We've got a course about Fibonacci numbers and rabbit populations, more arithmetic and geometric sequences, lots of real-life applications like Fibonacci numbers and the golden ratio in sunflower spirals. We've already played with the Königsberg Bridges problem. This is about planar graphs and determining which graphs are planar, which aren't. Some interactive probability, and you can sort of roll thousands of dice at once and see different distributions. You might know the Monty Hall problem, famous sort of probability puzzle, and you can actually play this and several times and see what happens, or play roulette and determine whether the wheel is rigged or not. We've got some courses about origami and different origami axioms. Here students can derive formulas for the surface area of cones and cylinders and see conic sections in action or map projections. We've got a little bit on chaos theory, which again we briefly mentioned in the workshop, transformations and symmetry. One of my favorite activities is about wallpaper groups. These are sort of repeated two-dimensional patterns, and students can draw their own patterns here. They can pick one of the 17 different wallpaper groups and draw these really beautiful patterns. Some stuff about prime numbers, Pascal's triangle, more sequences, and can find the Sierpinski triangle hidden in it. Students can construct their own geometric shapes, see different proofs of Pythagoras' theorem. I think in lesson 6 today, James Tanton will be talking about exploding dots, which again, you saw a very brief snippet about before. We've got lots of virtual manipulatives like polygons or number tiles, algebra tiles, tangram you can use in classrooms. We've got an entire timeline of mathematicians if you're interested in the history. Factris is a game we developed recently, which is about factorizations. And yeah, some more origami and 3D polyhedra. And yeah, I think that's it. We are almost out of time. Thank you so much for listening. Please email me or tweet me if you have any questions, any suggestions, feedback, and so on. And I hope you really enjoy the remaining talks today.